Hello Math 2000, Linear Algebra. It's Professor Wenson here again with a video on the ZyBooks Section 1.2, Matrices and Linear Systems. So I'm not going to start off in Canvas. You know where hopefully the page for Section 1.2 is in Canvas with some extra videos to watch if you want. I'm just going to start straight up in ZyBooks, and we'll go through section 1.2, and I'm going to, I'll start some participation activities, I'll start some challenge activities, but for the most part, leave it to you to do. Okay, so this is matrices and linear systems. So again, you can read the summary and here are the objectives. Right? In this section, you will be able to, use matrix notation, identify the size of a matrix, identify special types of matrices, which is the plural of matrix. Find the transpose of a matrix. Find the trace of a matrix. And finally, represent a system of linear equations as a matrix. Alright, so first part's on matrix notation. A matrix is a rectangular array of numbers or expressions arranged in columns and rows. The size of a matrix is given by m by n. That's said mxn there. M by n, where m is the number of rows and n is the number of columns. Right? And rows are horizontal. Right? Columns are vertical. Rows are left, right. Columns are up, down. The entry in row number I and column number j in an m by m matrix, capital A, usually in this text, this ZyBooks text, a matrix will be represented by a capital letter. The entry in the row I and column j is written as a lowercase. If it's capital A, if the matrix is capital A, any entry within the matrix is usually represented by a lowercase version of that with a subscript. And the subscript tells you what row and column you're in. So for instance, A11 here, that's the entry in row 1, column 1, right? First row, first column. A12, right? The entry in the first row, second column. First row, the second column, and so on. That's A. So Aij is the entry in the ith row and jth column. So you can write the matrix A with a capital letter A, or just put in a little bracket, like the matrix brackets, and have what every entry looks like with a little Aij like that. Right. Whereby the size of A is understood from the context. All right. Two matrices are equal if the matrices have the same size and the same corresponding entries. Right, so the first, if you have two matrices that are both 2 row, 3 column, 2 by 3, they're going to be equal if they're both 2 by 3 and, the first row, first column entry in the first matrix is the same as the first row, first column entry in the second matrix, and so on until the second row, third column. Every corresponding entry is the same. All right, so I'm not going to, again, you got a participation activity to complete. Hit start, play through the animations and stuff until this upper box is completed. You can see here this is a 4 by 5 matrix, right? You see there are 4 horizontal rows, 5 vertical columns, right? 4 by 5, and it's always row by column, horizontal lines by vertical lines of numbers or entries. Okay? Pardon me. All right, so you have another participation activity here. Now I'll do a couple of these. And again, pretty easy. All you're doing is determining the size of the matrix. So you got these rectangular brackets here to indicate that it's a matrix. 318 is the first row. 0, -4, 5 are the entries in the second row. This has 2 rows. Then column 30, column 1, -4, column 8, 5, 3 columns is a 2 by 3 matrix. And it'll explain and fill all these in. this would be a 3 by 3. This is a 1 row, 3 column, right? And so on. And this is 4 row, right? 4 rows, 4 horizontal, 1 column, right? And then the challenge is just the size of a matrix. So again, pretty easy to just fill in some. Now you can use the little arrows here. This is a 3 horizontal, 5 vertical, right? 3 row, 4 column. So I just use the arrows here if I want, or just enter the number with my keyboard. So that's a 3 by 5 matrix. Great. Move on to the next thing. All right, there are 4 problems here in this challenge activity. And again, this would be a 4 by 4. 4 rows, 4 columns. Right? 4 by 4. And I'm not going to do it, I'll just do these two. Right? And you're not going to see the same exact problems that I am, right? But the type of problems you will see is the same as the type of problems I'm seeing here. All right, and I'll move next if I want. All right. Now some definitions. A diagonal entry, Aij, remember this is the entry in the ith row, jth column. A diagonal entry of a matrix A, or whatever the matrix is called, is an entry where I equals j. So a diagonal entry is just all the entries where the row number and the column number are the same. So A11, A22, A33, A44, etc. Those are the diagonal entries of a matrix. The main diagonal of a matrix consists of all the diagonal entries. So like this matrix here, the main diagonal consists of the entries -5, 12, -10, and 8. Right? That's A11, A22, A33, A44. Right? Where all those entries where the row number and column number are the same. All right. A zero matrix is a matrix in which all entries are 0. So if every single entry is a 0, they call it a zero matrix. A column matrix, sometimes referred to as a column vector, which we'll see much later, is composed of a single column. So it's got, m rows, but 1 column. A row matrix, again later we'll see this sometimes referred to as a row vector. A row matrix is composed of a single row, right? So 1 row and n columns. Right? A square matrix has the same number of rows and columns, so it's n by n. For example, this one right here, this is a 4 by 4. This is a square matrix. And a diagonal matrix is a square matrix in which all non-diagonal entries are 0. So right here, look at this one. Here's a square matrix, 3 by 3. All the entries that are not on the main diagonal, right? The main diagonal has the 1s here. All the entries not on the main diagonal are 0. So this should be considered, this I3 here, would be considered a diagonal matrix. Right. An identity matrix, I, is a square diagonal matrix in which the entries along the main diagonal are 1, and since it's diagonal, all the other entries are 0, all the ones not on the main diagonal. The n by n identity matrix is written as I sub n in this book. I2 then is a 2 by 2 identity matrix, so 1's down the main diagonal and 0 everywhere else. I3 is the 3 by 3 identity matrix, 1's down the main diagonal, 0 everywhere else. Okay. All right. And again, entries of a matrix, you can again just hit start and it'll play some animations and whatnot. And it's just describing to you what a matrix is again. And then the next one talking about how to find an entry, right? Ith row, jth column, right? Row 1, column 2, that chunk, A1, 2. It's going over all the stuff I've been explaining. All right, types of matrices, examples. All right, so look at part A. This is a 2-row, 4-column, 0 matrix, right? Every single entry is a 0. Here is a 3 by 1, 3 rows, 1 column. Since it's only got 1 column, it's called a column matrix. Here is a 1-row, 3-column row matrix, right? Since it's only got 1 row, sometimes called a row matrix. Here's a 3 by 3 matrix. It's square, right? 3 rows, 3 columns. Same number of rows as columns is square. Here's an example of a diagonal matrix, right? The main diagonal entries are 3, -1, and 0. But what makes a matrix a diagonal matrix is if it's square, 3 by 3 like this is, and all the non-diagonal entries are 0. So the ones off the main diagonal are 0, which you can see here, right? First row, second column, first row, third column, second row, third column, second row, first column, third row, first column, third row, second column. All those are 0s. And this would be the 4 by 4 identity matrix, or I4 in this book. 1's down the main diagonal and 0's everywhere else. All right, so activity. Again, I'm not going to do all of them, just a couple. So here's your matrices here. A is a diagonal matrix. No, first of all, a diagonal matrix, by the definition here, right, it has to be a square matrix, first of all. Right. So that's not even a square matrix, so it can't be a diagonal matrix. Right? A diagonal matrix must be square. Right? And then have 0s on entries that are not on the main diagonal. A12 equals 3. So this is the first row, second column entry of matrix A, right, is 3. So look at matrix A. The first row, second column entry is not 3, it's -2. So this is also false. Right, and you say it's -2, not 3. Let's see, there's like, I'll do like 5 or 6 of these. A23 is 4. That's the second, it's little a, so it's for matrix A. The second row, third column entry of matrix A is 4. Let's see. Second row, third column entry, that is 4. This is true. Matrix B is a diagonal matrix. Yes, all right, it's a square matrix, and all the entries that are not on the main diagonal are 0s. So yes, that is a diagonal matrix. The number 0 is a diagonal entry of B. Well, look at matrix B. The diagonal entries are where the row and the column are the same. So first row, 1, 1, 2, 2, 3, 3, that's 6, -3, and -4. None of those are 0. So this is a false statement. All right, and again, hopefully you could do the rest based on definitions. Okay, the transpose of a matrix. Now this is pretty simple to write. All right, the transpose of a matrix A, written A to the T. I know it looks like a power, but it's not. It's just A with a superscript of T. This means A transpose, or the transpose of A, is the matrix that has as rows the columns of A. So basically the rows of A become the columns of A transpose. See how row 1 in matrix A here, A11, A12, A1J, A1N, becomes the column, the first row of A becomes the first column of A transpose. See the A11, A12, A1J, A1N. The second row of A becomes the second column of A transpose, and vice versa. Right? So thus, if A is an M by N matrix, A transpose is an N by M matrix. The size switches. So if a matrix is 2 by 3, its transpose will be 3 by 2, for example. All right, and they take you through an example here as well, where you can, again, watch an animation. All right, so here, this time I'll actually go to some pen and paper, and I'll also show you on a calculator how to enter a matrix on a. I'm using TI-84. Right, 83, 84 are very similar. I'm going to write just one of these. Right, just this part A. Okay, so here is the matrix from part A. Right, this is a 2 by 3 matrix. Right, 2 rows, 3 columns. And I want to write A transpose. Right, so A with this T above it. So I put the rectangular. Now, if A transpose, if A is a 2 by 3, A transpose is going to be a 3 by 2. 3 rows, 2 columns. All right, and it goes like this. The first row of A, negative 1, 0, 2, is the first column of A transpose. The second row of A, negative 2, 3, negative 4, is the second column of A transpose, negative 2, 3, negative 4. And there you go. This is A transpose, the transpose of A. Now the same thing goes for the entries, right? Like over here, what's the second row, third column entry? A23 is negative 4, right? All right. Over here, let me call this matrix B, because it is a different matrix, right? If you remember, matrices are only the same when they have the same size and the same entries in corresponding positions. So it's a totally different matrix. I'll call it matrix B. What's B? A23. I switch these. 3, 2. What's B 3, 2? Third row, second column is again negative 4. These should be the same, right? When you do the transpose, you just switch the row and column, right? Switch rows and columns. Okay. Now, there's also a way you can do this on your calculator with some entering matrices and getting the transpose. And let me show you that. So here I'm pulling up my emulator for the TI-84 Plus. Turn it on. This is some previous class. So if you want to enter a matrix into your calculator, if you have an 84 or 83, if you have something else, just Google it. You go above the X inverse, or this X to the negative first button, there's a thing that says matrix. You go second, matrix. And move your cursor over to edit, right, because I want to make one. And it doesn't matter which one you pick, just pick an empty one or one that's already there. Hit enter on A, number 1. Then it's going to have you enter the size of the matrix. See, rows by columns. My matrix A here was a 2 row, 3 column. So I go 2, enter, 3, enter. And you see the 6 spots fill in the 2 rows, 3 columns. And now it's having me enter the first row, 1, 1. First row, first column entry is 0 right now. I want it to be negative 1. So I go negative 1, enter, and then just go through, first row, second column, and I'm going to enter these in. All right, so 0, it's already there. 2, negative 2, 3, and negative 4, right? All right, so now I'm going to get out of here, go quit, second quit there. And I'm going to have that matrix show up on the screen, on my calculator screen. So I go back to the matrix menu, and then under names, I can just enter matrix A now. This is the one I edited, and there you go. See, it's this matrix with negative 1, 0, 2, negative 2, 3, negative 4. But now I would like the transpose of A to be on my calculator. How do I do that? All right, so second, go back to the matrix menu. Over and enter the matrix you want to take the transpose of, matrix A, and then back to the matrix menu, and then over to math, where it says math. And then you see the second thing where it says T there, that little T. Scroll down to that, or just hit the number 2. And this is A, matrix A, but the transpose of it. You see that? A 1, negative 2 for the first row, 0, 3 for the second row, 2, negative 4 for the third row. The rows of A became the columns of A transpose, or the columns of A became the rows of A transpose, however you want to think about it. Okay. Let's get rid of that now and go back to the thing. Right. So we found that for A. Now A, B, C, D, this is a 2 by 2, will be another 2 by 2, but the transpose will have, A, B as the first column, C, D as the second column. Right? The transpose of this is a 3 by 1 will be a 1 by 3. So negative 3, the first column here will the column will be the row negative 3, 0, 1 in the transpose. And the transpose of the identity matrix is itself, as you can see, the transpose of a diagonal matrix. Any diagonal matrix is going to be itself. You can see that hopefully. All right, some more problems here. Now, I'm just going to do the first one here. The transpose of a 2 by 4 matrix is a 4 by 2. Yeah. Right. Okay. This one too. 1 0 is this A transpose? If this is A, would this be A transpose? No, right? 1 0 3 should be the first column of A transpose. The first row of A should be the first column of A transpose. That's not happening. And show you what it should be. All right. This is not an identity matrix. Be careful, right? This is a 3 by 4. So the transpose should be a 4 by 3. Be careful. All right. More transposes. Now they're just asking for size here. Now there's 6 problems in this challenge activity. This is a 2 by 3. So the transpose should be a 3 by 2. All right, I'm going to show you what it should be. All right. This one is actually having you fill in the entries. So first row, first column, switch them. It's still 1 1, so 4. The first row, second column of A transpose would be the second row, first column of A, so 1. The second row, first column of A transpose would be the first row, second column of A, negative 3. The second row, second column of A transpose would be the second row, second column of A, right? The diagonal entries don't get moved. They don't change position. The third row, first column of A transpose would be the first row, third column of A, 8. Oh, I'm sorry, first row, third column, 3. First row, third column. And then the third row, second column of A transpose would be the second row, third column of A, 8. All right. And again, notice the first row of A is the first column of A transpose. The second row of A is the second column of A transpose. Okay, so I think that's enough of that. You got 4 more of those. All right, now the trace of a matrix is even easier, I feel, to determine. The trace of a square matrix, okay, it's got to be square to be able to calculate what's called the trace, denoted by this tr of A, the trace of matrix A, TR, is the sum of the entries along the main diagonal. So the trace of a matrix is, remember this, whenever you see this sigma, that means you're adding up things, right? The sum from I equals 1 to n of AII, so A11 plus A22 plus A3 all the way up to ANN. You're just adding up all the entries down the main diagonal, all the diagonal entries, all the ones where the row and column are the same. And that's the trace of a square matrix. The trace of a non-square matrix is undefined, right? It is not defined, the trace of a non-square matrix. So examples here, you can read those. All right, so now this is fill in the blank. Ooh, right, not fill in the blanks here for this participation activity. Find the trace of each matrix. If the trace does not exist, type as DNE. This is a square matrix, 2 by 2, so it has a trace, and it's just the sum of the main diagonal entries, 1 plus negative 3, negative 2. And I check. Great. This is not a square matrix. This is a 2 by 3 matrix. So DNE. The trace does not exist. Okay, pretty easy. All right, and finally, the last topic is the matrix representation of a system of linear equations. So we saw last section what a system of linear equations looks like in n variables. If you write them in this form, right, the forms that linear equations, a linear system took in the last section, you'll see that all the x1 terms are lined up, all the x2 terms are lined up, all the xn variable terms are lined up. You have your equal signs, and then your constants, all these b's on the b1 through bm over here. So you got to make sure that's the way that the system looks before you can go into writing matrices related to that system. All right. The coefficient matrix is given by it's a matrix, an m by n matrix made up of the coefficients of the variables. See down the first column, a11, a21, am1. These are just the coefficients of x1. Down the second column, a12, a22, am2. These are just the coefficients of x2, and so on till the last column. These numbers here, a1n to amn, these are the coefficients of the nth variable xn. Right? Let me show that here. The matrix of constants. You can make a matrix with a column matrix, right? With one column of just the constants, b1 through bm on the other side. Right? That's called the constant matrix. Matrix of constants. An augmented matrix is formed when two matrices are combined, and usually a little bar will be written to show the separation between the matrices when they're combined. And you'll see in a later sections, augmented matrices are useful when solving a system of linear equations. All right. So we're going to create augmented matrices to represent, right, a system of linear equations where one of the matrices is the coefficient matrix, and then the matrix that's added on to augment it is the matrix of constants. So let me show you what I mean. I'll actually write. You can see here. You can play. You got to play the animation, complete the activity. Here are three linear equations in three variables: x1, x2, and x3, and they're written in the standard form where the x1s are lined up, x2s, x3s. You have your equal signs, and then your constants: 2, -1, and 0. So you see the coefficient matrix is made up of the coefficients of the variables, where down the first column I have 3, 0, and 1, the coefficients of x1. Down the second column, -2, 2, 0, the coefficients of x2. Down the third column, the coefficients of x3, 2, 1, -1. And then if you draw a little bar in here and add to that to augment it, make it an augmented matrix, on the other side of the bar kind of represents the equal signs, if you want to think of it that way. And then you have the augmentation, 2, -1, 0. That's the matrix of constants on the other side. So I'm going to do that for this example here in the participation activity. Okay, so I've written out this system in the participation activity here. Okay. And it's all these linear equations are set up in standard form where all the variable terms on one side, constants on the other side of the equal signs. Now the matrix representation of this system is an augmented matrix. I'm going to write the little matrix symbol, a little square bracket there, where I'm just on the left side I'm putting the coefficient matrix, the coefficients of the variables, then a little bar to represent the equal signs where the equal signs are, and then another matrix on the other side, the matrix of constants, add it on to augment it. So down the first column here, the coefficients of the first variable, x1. So in the first equation I have 2x1. Next equation, 3x1. And then the third equation, right? In the third equation there isn't an x1 term, so technically there's 0x1. Right? You can always throw on none of something, it doesn't really affect anything. So 2, 3, and then the entry in this part of the matrix, the third row, first column, would be 0 for 0x1. Then down the second column, the second column of the matrix will be the coefficients of the second variable, x2. So the first equation, for the first row, second column, positive 2. And then negative 3. Then positive 2 again. All right, they're the coefficients of x2. All right, then the third column of the matrix will be the coefficients of the third variable, x3. Again, this is when everything's in standard form, like this is, and everything's stacked up nicely. Positive 7, negative 2, negative 1. All right, and then what I've just written here, right, if I were to close it off and write the brackets, right, what I've just written, this is the coefficient matrix, right? Just the matrix with all the coefficients of the variables. Right? Just this this is a 3 by 3 here. But I'm going to make it into a 3 by 4 by adding something on, augmenting it. Put a little bar here, kind of representing where the equal signs would be. And then on the other side, I'm going to put the column matrix, the matrix of these constants. 3, 4, negative 3. Right. And so over here, this is the matrix of constants, or constant matrix, whatever you want to call it. Right. And this would be the coefficient matrix is a 3 by 3. The matrix of constants is a 3 by 1. But the whole thing, right, the matrix as a whole is a 3 by 4 matrix. Right? So the coefficient matrix is a 3 by 3. If you were to look at that on its own, the matrix of constants, if you were to look at this matrix of constants on its own after the bar, is a 3 by 1. But the whole thing, right, the whole augmented matrix is a 3 by 4, 3 rows, 4 columns. And that's it. It's as simple as that, right? Just writing a bunch of numbers that you see in the system. All right, so looking at this, just what would the value of A have to be? Positive 2. Right, so I'll fill that in, enter, and I'll let you do the rest. Okay. Challenge activity, you're making one of these matrix representations of a system. You're filling in the blanks for an augmented matrix. So I'll start this here. So see how it's already, the equations have to be in this standard form, right? With all the variables on one side lined up with like terms, lined up nicely, and all the constants on the other. And then you can create these augmented matrices. So I got what, negative 6x1, then negative 3x2 in the second column, then a little bar where the equal signs would go, and then 3 for the constant, all that in the first row. And then for the next equation, you have negative 8x1, so negative 8, plus 6, so positive 6x2, bar equals, and then 7. Right? And this 2 by 3 matrix here, 2 rows, 3 columns, represents this system. All right, and the reason we're doing this is so we don't have to keep writing the variables over and over and over again, right? Because that'll get a bit tedious, and writing just the matrix with just the numbers involved and keeping in mind what each column means. You know the first column is for x1s, you know the second column is for x2s, you know the bar means equals, and you know the third column is for the constants. It'll make things a lot easier when we go into solving these systems. And I think that's all the challenge activity is here. Let me see what the next level looks like. Yeah, it's exactly the same thing. Alright, just filling in the blanks with the coefficients. And again, make sure that these equations are in the proper form. If they're not in the proper form, get it in the proper form, where all the variables are lined up on one side and the constants on the other. Alright, and then again you have your additional exercises where you see it. You'll see assignment in assignment 1 from week 1. Some of these additional exercises I've assigned to you. You can see the solutions here if you want to check yourself. Right? But you're going to write that stuff out on paper and then upload it to me in the assignment 1 page. And I would also recommend trying to do the exercises here that I didn't assign, right? Just for some extra practice, and get used to the material. All right, so that's it for section 1-2, and thank you very much for watching. Hope it was informative.